Today, before we go into the concept or the idea about real numbers, first we shall look upon the most basic and most important natural numbers first. Alright, so the chapter is real numbers. But first we shall look upon the concept or the idea about natural numbers first. So first we should talk about natural numbers. And so I hope that you've all come across these natural numbers right from class KG1, KG2 and class 1 and so on and so forth. Right? So natural numbers, or sometimes these are also known as counting numbers. Natural numbers or counting numbers. Why are they called counting numbers? Because we usually use these numbers for counting, right? And these numbers are 1, 2, 3, 4, 5, 6, and so on. Alright, it does not end till 6. To get the next natural number, you just have to add plus 1 to the preceding number. For example, you want to find the next natural number after 6, so you just add plus 1 to 6, you'll get 1, you'll get 7. So the next natural number after 6 is 7. Alright, so let's move on to the next group of numbers, which we call whole numbers. So whole numbers is not that different from natural numbers. You just have to include 0 to the set of natural numbers. Natural numbers including 0 are called whole numbers. Alright, so let me just write the set of natural numbers including 0 called set of whole numbers. I know I've introduced a new term here which is called set. Don't worry, let me explain to you what this word means. You'll be doing this more clearly in class 11, so let me just give you an easy definition of a set. This is actually the proper definition of a set also. A set is a collection of well-defined objects. I will explain to you what well-defined means. But first of all, we can clearly understand collection means we collect something. Alright, it may be when we talk about a set, it doesn't usually mean that we talk only about numbers. We can include things like chairs, tables, etc., or even persons. Alright, like a set of boys of age under 8 years, something like that. Alright, so let me just give you an example of what a set is. Alright, let A be the collection of all positive numbers. Alright, so let me explain to you why this collection, alright, we're collecting all positive numbers, why this collection is called a set. First, let me explain to you what well-defined means. Well-defined simply means that you can say or you can tell whether an object which you have collected belongs in that collection or not. Alright, for example, in this collection, let A be the collection of all positive numbers. If you take any number, since we are talking about numbers, if you take any number, for example, 1, you can tell, right, whether this number belongs or not in this collection A. It obviously belongs because why? 1 is a positive number, and this collection is the collection of all positive numbers. For example, you can, if you take another number, 2, this also obviously belongs in this collection. If you take another number, -3, see, if you take -3, we can clearly say that this -3 does not belong in this collection because this collection is just the collection of all positive numbers. So that's what the word well-defined means. You can tell whether an object, in this case we're talking about numbers, so you can tell whether this number, or any number belongs in that collection or not. Alright. So when I use the word set here, it's just a collection. So whole numbers is what? It's just a collection of natural numbers including 0. Alright. So let's move on to the next group of numbers, which we call integers. So let me just give you the definition first. An integer is a number which is a whole number and by whole number I don't necessarily mean that these are whole numbers. For example, like whole numbers, they start from 0, 1, 2, 3, 4 and so on. Alright. By whole number, here in this definition of integer, I mean that it's not fractional. Which means it should not be of the form 1 by 2, 2 by 3, 4 by 5 and so on. Alright? So an integer is a number which is a whole number, and may be positive, negative, or 0. Alright, so an integer is what? It's a number which is a whole number, and by whole number I mean it's not fractional. Alright, I've already explained to you what not fractional means, and maybe positive, negative, or 0. So let us just look at some examples of integers. 0 is an integer, it's clear from this definition, and 1, 2, 3, these are all positive, they are not fractional. Alright, these are not fractions, so these are also integers. So integers can also be negative numbers, so we can also take some examples like -1, -2, -3 and so on. Alright, so let me move on to the next group of numbers, which we call rational numbers. Alright, so let me just rub off this part. So what are rational numbers? Let me go first to the definition. A number which can be expressed in the form P by Q, where P, Q are integers and Q should be not 0, and Q not equal to 0 is called a rational number. Alright, so it's not that difficult to understand what are rational numbers. These are just numbers which can be expressed in the form of P by Q, where P and Q are integers, which we just did right now, and Q should be non-zero, alright, because division by 0 is not allowed. And so let us take some examples of rational numbers. First you see natural numbers, alright. Are natural numbers rational numbers? See, the first natural number is 1. This is a rational number. Why? Because 1 can be expressed in this form, P by Q. See, we can write 1 in us. 1 is equal to 1 by 1. It's the same, right? So we clearly see that 1 can be expressed in this form, P by Q, where P and Q are integers, and this Q, alright, this is P. We can consider this as P and this as Q. We clearly see that Q is non-zero. So 1 is a rational number. 2 is a rational number because 2 also can be expressed in this form, alright, which is 2 by 1, 3, 4, and so on. So natural numbers are also rational numbers. What about whole numbers? Whole numbers also, because for whole numbers you just include 0, right, to the set of natural numbers. So a whole number also, 0 can be divided by anything, right, except 0 itself. So you can write 0 by 1, 0 by 2. It can be expressed in this form. So whole numbers are also rational numbers. And so what about integers? Integers also is very easy. Integers also are rational numbers. Why? Because every integer can also be expressed in this form, P by Q, where P and Q are integers and Q is not equal to 0. We just divide by 1 to each integer, right? For 0 you can divide by anything. So let me just divide it by 1. So we clearly see that integers also can be expressed in this form, P by Q, where P and Q are integers and Q is non-zero. So we see that natural numbers, whole numbers, and integers are also rational numbers. So all these natural numbers, whole numbers, and integers can be included or grouped together in the set of rational numbers. Alright? So now let me introduce you another definition of rational number. Because if you just go by this definition, there will be some numbers in which you cannot tell whether they are rational numbers. Alright? So let me give you an example of such a number. Example, let me take this example, 0.123, 123, 123, and so on. Alright? You see, this number is when I write this dot dot dot, it means that 1, 2, 3, it keeps on repeating. Alright? This number, these numbers 1, 2, and 3, it keeps on repeating. Alright? It never ends. Alright? So we see that this number, it's really hard to express this number in the form of P by Q, where P and Q are integers and Q is not 0. So in order to check whether this number is rational or not, it's really hard to go by this definition. Alright, so that's why we introduced a new definition of rational number. And that definition is numbers which have a terminating which have terminating or non-terminating but repeating decimal expansion are called rational numbers. So now if we go by this definition, it's clear that this number is a rational number. Why? Because even though this is, it's not terminating, because one definition is that it should be terminating, alright, but the other definition is that it should be non-terminating but repeating, alright. We clearly see that this number is non-terminating but repeats. Why? This number 1, 2, 3 keeps on repeating itself. This number you can write it as 0.123 bar. When I put a bar on top of here, it means you just check whether that bar starts from where. If it starts from 1, that means it will keep on repeating from 1 onwards. Alright? It ends to 3, so it will end at 3. And it goes on like this, 0.123, 123, and so on. So we clearly see that we need two definitions of rational numbers, because if we just go by this definition, there are some numbers which we cannot tell whether they are rational or not, and so we introduce another definition. Alright, so let me move on to the next group of numbers, which we call irrational numbers. So irrational numbers, the first definition is just the opposite of this one. A number which cannot be expressed in the form p by q, where p and q are integers and q not equal to 0 is called a rational number. So I won't write down the definition because it's just the opposite of this one. You can clearly write down it by yourself. So, but if you go by that definition also, it's hard to think of an example of an irrational number. I mean, numbers which cannot be expressed in the form p by q. Alright, so we introduce another definition of irrational numbers. Alright, so let me just write down that definition. Numbers which have a non-terminating and non-repeating decimal expansion are called irrational numbers. Alright, so let us take some examples of irrational numbers. So an example of an irrational number is like this: 0.01, 001, 001, 0001. You just keep on increasing the number of zeros, alright? You just keep on increasing the number of zeros. Then you can clearly see that this decimal expansion does not end, does not terminate, or does not end, you can say, does not terminate, as well as does not repeat itself. Why? Because the number of zeros keeps on increasing. Alright, so this is one example of a irrational number. Let me give you another example of an irrational number: √2, √3. Alright, since you all know how to find the square root of, right, of any number, so actually √2, when we find the square root, we find it is 1.414, but it does not end there. Alright, we just take the value till 1.414, but it does not end there. Remember, if you find the exact value of √2, it will be a number which has a decimal representation which is non-terminating as well as non-repeating. That is why root 2 is considered to be an irrational number. Root 3, root 7 and so on, these are also irrational numbers. Why? Because we go by this definition, numbers which have a non-terminating and non-repeating decimal expansion. Alright? So, I think now maybe you have a question that why is pi considered to be an irrational number? Because sometimes in the book we see that pi is sometimes taken to be 22/7, but we clearly see that 22 is an integer, 7 also is an integer, and 7 is not equal to 0. So that means pi should be considered to be a rational number, right? But instead we say that pi is an irrational number. Alright, so let me explain to you why we consider pi to be an irrational number. To find the value of pi, actually, we have to consider a circle. You can take any circle, consider any circle of any radius. Suppose I take R, and then to get the value of pi, you just have to take the ratio of the circumference of the circle to the diameter. Alright, so let's find out that ratio. Circumference. Let me just write circumference, but here the context is that it's the circumference of the circle. Circumference by diameter. So we know that the circumference of a circle is what? The formula is 2 pi r, and the diameter is twice.